Hello everyone and welcome back. Davide here. In this new video tutorial we are going to talk about the multiscale proper orthogonal decomposition in Modulo. We are almost at the end of this short course about Modulo. In this video we will perform the mPOD on the same cases that we have seen in the previous videos, so the 1D pulsating Pascal flow and the 2D time-resolved PAV. So let's start. As usual, we have to set an exporting folder. We start with the 1D test case, so select the testing modulo on the desktop and create another folder called test mPOD 1D. And now import your data. I will speed up this part of the video. Okay, D is ready and we can perform the mPOD. By choosing the mPOD, a new panel will appear. This panel allows for setting the mPOD parameters and in particular is dedicated to the multi-resolution analysis of the temporal correlation matrix. As you know from the third video tutorial dedicated to the theoretical background of this decomposition, the philosophy of the multiscale proper orthogonal decomposition is to perform the standard POD at different scales. Each scale covers a different range of frequencies. The frequency content in each scale does not overlap with the one of the others, and they cover the full spectrum. Therefore, the sum of all the scales recovers the entire energy content of the data. If we denote as m the number of scales, the partitioning looks like this. Here we have the frequency axis, and here is the Fourier transform of a signal at a certain location. This splitting is obtained using a filter bank composed of a low-pass filter to get the scale H1, a high-pass filter to get the scale HM, and the m-2 bandpass filters to get the intermediate scales. The cutoff frequencies of these filters are collected in an input vector that we call frequency splitting vector. So the first important parameter is the number of scales. You can introduce this parameter from this input here. However, observe that in the current implementation we don't count here the lowest frequency scale, which is always taken into account by default. Hence, this parameter indicates the additional scales required by the user. For example, if we put here 2, then we split the domain in 3 scales. Note that to limit the computational cost, in the current version you can introduce here at most 10, that corresponds to 11 scales. If much finer splitting is needed, then the mPOD might not be the best decomposition for your scopes, and you should consider harmonic decompositions such as the DFT. So, how can we choose the best number of scales? Well, although we are working on several algorithms, there is currently no best option. You should have a look at the spectrum of your temporal correlation matrix and define the splitting based on the phenomena you want to isolate. To plot the spectra of the correlation matrix, we first should introduce the sampling frequency, that for this test case is 2. Always remember that the unit is not specified in the GUI because it depends on the dataset. In this case, it is dimensionless. As you can see, by editing this value, the figures in the bottom part of the panel change. On the left, a contour plot shows the magnitude of the cross-spectral density matrix, while on the right, the normalized spectrum of the snapshots is plotted. This is the diagonal of the cross-spectral density matrix. For plotting purposes, we can change these two parameters, c-axis and frequency axis limit. By editing the frequency axis limit, we just readapt the boundaries of both plots. This value is changed by default as we change the sampling frequency. Its default value is the half of the sampling frequency plus fs over 10, since all the frequencies involved are in the range from minus fs over 2 to plus fs over 2, with a resolution delta f of fs over nt. By editing the c-axis values, the resolution of the plot on the left improves. Here we can appreciate the correlation between the frequencies involved. These plots are the key to choose the frequency splitting vector. For now, don't pay attention to the red line in the spectrum and to the checkbox Fast mPOD. I will come back to this shortly. So in this case we can zoom a bit more to see which are the frequencies of interest for this case. We have clearly two dominant frequencies. The first is close to 0 and the second is close to 0.2. Observe that the data is real, so this spectrum should always be symmetric around the mean, that is the frequency 0. At this stage we cannot run the decomposition, since we first need to define our frequency splitting vector. We click on the Set button to proceed with the setting. Before going ahead, we set the axis limit to 1 to better see the full plot. In the first window that appears, we can introduce the frequency splitting vector. The number of elements of this vector depends on the number of scales. In this case, we have two additional scales, if we don't count the low pass that is taken into account by default. So we need to introduce two values. This means that the filter bank will work on three range of frequencies that are the default low pass filter from 0 to f1, and the bandpass from f1 to f2, and the high pass from f2 to the Nyquist frequency. Usually Modulo proposes default values that in this case are 0, but only because of rounding to integers, since the sampling frequency is near 0. But we can change them. If these are not integers, use points as decimal separator. So we can set 0.1 and 0.3, for example, so that we distinguish the two dominant frequencies. Just pay attention to some important detail. First, they have to be sorted. Second, the last frequency, theoretically, has to be at most the half of the sampling frequency, but in order to avoid leakage, it has to be less than fs over 2 minus nt over 5 times the resolution delta f. Then we are asked to input the length of the kernels, also proposed by Modulo. This is the order of the filters used in the bank. Larger values give sharper cutoff, but increase the computational cost and the risk of frequency leakage. Normally, the proposed values are good, but we can change them, for example, with 500. Note that these have to be integers. The last parameter is the keep vector. This vector can be set to use the mPOD decomposition as a filter. By default, it is a vector of ones. Namely, we keep all the kernels. Selecting the kernel means that the corresponding scale will be included in the decomposition, while if we don't select it, the corresponding scale will be discarded when assembling the final basis. Remember what we said before, that the lowest scale is always kept. So if we here set everywhere 0, just like this, then only the lowest scale will be kept, and the result would be equivalent to perform the POD of a low-pass filtered data with cutoff from the first entry of the frequency splitting vector. Now select both of them and click on OK. As soon as we complete this set of parameters, the Run button is enabled and the normalized spectrum changes. First of all, for plotting purposes, now only the positive part of the spectrum is shown, since it is symmetric. In the same plot, we can see also the kept modulus of the transfer function for each scale. So the red curve, that is the low pass, the yellow curve, that is the band pass, and the purple curve, that is the high pass. If, for example, we set the keep vector to 0 somewhere, the corresponding kernel will be removed from the plot, as shown in the figure. We can now talk about the red line you have seen before. This is the cutoff for each scale that can be modified manually from this input here. By editing the cutoff, we can reduce the number of computed modes that is shown in this string, mPOD modes estimation. What is the cutoff? This is used in each scale to define the number of modes from each scale that will be used to construct the final mPOD basis. If we put here 5%, it means that only the first NM modes that have at least 5% of the energy of the first mode will be included in the decomposition. Now, notice that for plotting purposes, we can modify the frequency axis limit and also the c-axis. But if we modify the sampling frequency or the number of scale, we have to reset all the parameters and the run button is disabled. This is done because if we change the number of scales, for example, then we should change also the filter bank, so the frequency splitting vector. As well, if we change the sampling frequency, then potentially we might change the values of the frequency splitting vector, even if the scales are not changed. Now reset the parameters to perform the mPOD. So the sampling frequency is 2, we need 3 scales, the cutoff is 10%, and now click on the set button to set the frequency splitting vector 0.1, 0.3, 500 as length of the kernels, and keep both of them. So click on the run button. When we run, a dialog summarizes the parameters. We can abort and reset them, or we can confirm and perform the decomposition. It starts performing the diagonalization of all the contributions of k, so at each scale. This is done to compute the temporal basis. At the end, it completes all the modes. As for the DFT, we need to compute all of them, even if we want to export only some of them. Here I have to highlight an important aspect. For the POD and DFT, the range of modes that we can export is from 1 to nt, that is the number of snapshots. This is not the same for the mPOD. As it is shown in the mPOD parameters panel, we don't compute nt modes because of the cutoff. So the range of the modes that you can export for the mPOD is from 1 to the estimation that in this case is 257. Now export only the first 2 modes. As for the POD, Modulo exports the sigmas and then the spatial structures on the left and the temporal structures with their frequency content on the right. Now close this and let's take a look at the exporting folder. In the exporting folder, Modulo has exported as usual the file containing the mesh, the file containing the sigmas, and then also the files containing the spatial structures and the temporal structures. Now let's make a comparison between the mPOD modes just exported and the POD modes exported in the previous video. For example, these are the second POD mode on the left and the second mPOD mode on the right. It is immediate to understand that the mPOD is able to distinguish the contributions of the two introduced sources, while this was not possible neither with the POD nor with the DFT. In this case, indeed, the POD fails because the constraint of energy optimality has nothing to do with the two mechanisms introduced. On the other hand, the DFT fails because the modes are not perfectly harmonic. For example, the second mode only occurs within a certain time range, and the DFT cannot localize events in time. The mPOD allows to achieve the best compromise by having modes that have narrow frequency content, similarly to the DFT, but at the same time sufficiently large to have modes with temporal localization, as we can see in the temporal structure. Okay, we now move to the mPOD of the 2D TR-PAV test case. I will here show you how to perform the mPOD in 2 ways. The first will be the classical one, the one in the original article, and the second will be the fast mPOD. This is an algorithm under development that allows for performing the decomposition in a very efficient way. I first create another folder for the exporting of the results and then I import the data. So testing modulo, test mPOD 2D. Now I will speed up this part of the video. The sampling frequency for this test case is 2000 Hz. For the other parameters, we will take a splitting vector similar to the one in the original article. This is available on archive and I will leave its link in the description below. Keep in mind that in the article the splitting vector is given in terms of strual number. We will take 4 additional scales and the splitting vector will be 160, 320, 400, 600. Set 201 as length of the kernels and keep all the scales. From the spectrum we can see that through this splitting all the dominant frequencies are assigned to different scales. Observe that above 600 Hz there is nothing interesting happening, so for sure we are not going to have leading modes with frequency content in this region. For filtering purposes, you could think of removing this scale and the resulting decomposition would not change much. This is confirmed also if we look at the contour here. Maybe we change this value and we can see that above 600 Hz nothing interesting is happening. Now, run the decomposition and export the first 10 modes. I will not speed up this part of the video because I want to show you what is the computational cost required by the mPOD. As we have seen also in the 1D test case, in the basic mPOD algorithm, the code will first break the correlation matrix into various scales, then it will diagonalize each of these, and finally assemble the mPOD basis. Now let's wait for the decomposition. Okay, now as we did for the 1D test case, let's make a comparison between the mPOD modes just exported and the POD modes exported in the previous video. For example, this one on the left is the second POD mode, and you can see that its frequency content has a dominant region around 250 Hz. However, this mode also contains higher and lower frequencies. The lowest range is mostly linked to the structures in the wall jet region, while the higher one is linked to structures closer to the nozzle. In the fourth mPOD mode, as the allowed frequency bandwidth is reduced, we can better focus on the structures existing within the 250 Hz. These are large vortices evolving from the Kelvin-Helmholtz instability in the jet, as described in the article. Now, to close the video, I will show you how to use the fast mPOD algorithm. Please consider that this is still under development and its spectral separation is currently not as good as in the one of the original mPOD. So, we close this panel and without re-importing the data, we create a different exporting folder called test mPOD 2D fast. Let's set the same mPOD parameters as in the previous exercise, but I will speed up this part of the video. The idea behind the fast mPOD is to perform the decomposition in one shot. In the classical mPOD, you have seen that we first compute m correlation matrices, one for each scale, and then diagonalize each of these. In the fast mPOD, we construct a single filtered correlation matrix, the diagonalization of which yields in one shot the mPOD basis. You can activate this by simply ticking on this checkbox. If we now run, you will see that the code is much faster. I will speed up only the exporting part. If we now compare the mPOD modes, you can see that some of these remained identical. For example, this is a comparison of the second mode. This is the third mode. And finally, this is the fourth mode. They are all identical. However, if we look at the mode 9, we can see a spectral leakage that ruins the spectral separation of the decomposition. This is due to difficulties in preserving the MRA capabilities when acting on a single correlation matrix. I encourage you to try this first beta version of the fast mPOD on the other exercises, and you will see that such leakage does not occur frequently. However, with this test case, we simply wanted to warn you that this feature is still under development, and if you have enough computational resources, we suggest you to stick to the original mPOD for the moment. Well, this was the mPOD in Modulo. With this video, we have completed the overview of the decomposition methods implemented in Modulo. The next video will be the last of the course and will be dedicated to the memory saving option in Modulo. I hope you liked this video and I'll see you in the next one. Goodbye!